అప్పుడు ఏం చేయాలంటే ఆ లైట్ దీని మీద పడుతుంది కదా, లైట్ దీని మీద పడదు కదా. అప్పుడేంటి ఈ కెమెరా కొంచెం వెనక్కి పంపిస్తాము, ప్రజెంటేషన్ అవుతుంది. ప్రెజెంటేషన్ చూడండి. దగ్గర పెట్టాలి. చూడు చూడు ఒకసారి చూడు.
So, good morning, all beloved participants. So, I am Professor Venkatraj, former head of Department of Computer Science and System Engineering on the University College of Engineering. So, anyway, so nice introduction. Thank you, madam. I am seeing most of the participants physically, and the girls are women participants. So I also thanks all the participants who are online or virtually. So I don't know what happened yesterday. I think some of the basics or some of the fundamentals they have discussed. Anyway, so I would like to give some fundamental concepts. Then I will move to what is quantum computing and quantum computing algorithms, and what are the security issues. So basically, there are two powerful quantum computing algorithms: Shor's algorithm and Grover's algorithm. Anyway, we will clearly see these two algorithms with examples, right? And you can also work out these two algorithms using Qiskit quantum tool. So anyway, I will not do that. That will leave now because you need to download that software and you need to work out. Anyway, it's very easy. So later you can do it. Right. So before quantum computing and algorithms, what is computing? Is only calculation. Computing is only calculation, we want to say. Right. So you can perform some calculation, of course, processing information, storing data, executing instructions, right? So etc. Many things are there. Okay. So using computers and algorithms, we can process the information. It is nothing but computing. Okay. Using computers and algorithms, we can process the information. It is nothing but computing. So can anybody tell what are the applications of computing? Applications, at least one or two applications. There are many applications. One application, communication, email communication, message, videos communication. Nowadays we are all doing all this. Early morning we are opening our mobile, right? Observing WhatsApp, okay? and calling video call to your friends or parents or right, sister or brother. Okay, all these are, there are more education applications, there are commercial applications, there are several applications of computing, of course. So coming to classical computing, classical computers. Today we are using, everybody using classical computers, right? Classical computers and classical computing uses zeros and ones to perform or to process the information. Whatever the information we represent, that information is, data is represented by using zeros and ones. Okay? So every data is represented by using zeros and ones, and zeros and ones are processed. So classical computers use 0 and 1. You can understand that classical computers use 0 and 1. Right? So either 0 or 1. We are using either 0 or 1 to represent data. So group of these zeros and ones, we can form some data and we can process that data. Okay? So coming to another type of, anyway, there are 4 types of computing, everybody you know, right? Classical computing, any computing, cloud computing, HPC, high performance computing, quantum computing. So these are the 4 types of computing. Okay? So quantum computing, every day you know you are using classical computers and you are working with the computers for our general purpose to solve our problems, right? So any type of solving applications. So coming to what do you mean by quantum computing? In quantum computing, we can use quantum bits. Rather than using classical bits, we can use quantum bits. Quantum bits in the sense 0, 1. 0 is one state, 1 is another state, and combination of these 2 states is nothing but superposition. That is called superposition. Combination of these 2, for example, 0, 0, 0, 1, 1, 0, 2 state, right? So 2 qubits, for example, right? So 0, 0, 0, 1, 1, 0, 1, 1. So combination of these 2 states is nothing but superposition. It is called superposition. Okay, right. So coming to cloud computing, what is the purpose of cloud computing? Delivers on internet. Services will deliver on internet. So HPC, high performance computers, so use it to solve some complex scientific and engineering applications, problems. Okay, so anyway, coming to quantum computers, quantum computing uses 3 phenomena. One is superposition, another one is entanglement, and the third one is interference. Superposition, entanglement, and interference. So these are the 3 principles we can use in quantum computing. Okay, so already I told you what do you mean by superposition. Using combination of 2 states, right? So we can form superposition 0, 0, 0, 1 like that. And entanglement means, so there is a relation between 2 qubits. So for example, we can toss a coin, right? And after laying on the table or down only, we can say that at that time, right? So we cannot say after laying, right, toss a coin, you cannot say that, so you will get head or you will get tail, 50-50 chances. Okay, right? So for example, 2 coins are entangled by some means, connected by some means, right? So toss both the coins at the same time. So both must be heads and both must be tails. There are some connected, connected. These two coils are connected, right? So whatever the distance, there's no matter of distance. How much is the distance, right? So both will once laid down, right, on the table, both will tile or both will head. That is entanglement. Okay. So I will anyway will come to the interference later. So coming to then we'll explain. See, so there are some slides. We will go through the slides. But anyway, already I have covered this. What is quantum computing? The technology that uses quantum mechanics to process information. So quantum mechanics, I told you three phenomena we can use, right? Three principles we can use. Superposition, entanglement, and interference. So we can use qubits in quantum computing to process that information. Not classical 0 or 1, right? So we can use qubits in nothing but quantum bits. So by forming more number of classical bits, we can form qubits. So maybe 2 qubits or 3 qubits, 4 qubits, right? So like that, you can form qubits by using classical bits. Right? See that the peak inside. See, quantum computers does not replace classical computers. This is my statement. Quantum computers does not replace classical computers because classical computers we can use for everyday applications. Quantum computers are used only for specific applications and specific purpose. Right? So they solve a specific class of problems exponentially faster using quantum phenomena. I told you quantum phenomena, the phenomena. Okay? See, some comparison using classical and quantum computing. So coming to classical computing, we can use either 0 or 1 bits. In classical computing, qubit 0, 1 or both. Superposition, combination of both. And processing is sequential and parallel steps. How to perform parallel processing in classical computers by using multiple processors. A single processor can do only one task simultaneously, right? So sequentially it can do, right? Simultaneously you want to do more tasks, you can use more number of processors. Okay, so using multiple processors we can perform parallel processing is possible in classical computing. Anyway, quantum parallelism using quantum computers, right? All the states by using different states is possible, right? So quantum parallelism. And we can use logic gates in classical computers, and we can use quantum gates in quantum computers, Hadamard gate, to generate superposition. Okay? And the formula for many tasks in classical computers, exponential speed up for some tasks only, not for all the tasks. Right? And of course, error is very low in classical computers, and prone to decoherence sometimes when measuring the quantum qubits, quantum bits, sometimes it may collapse. Right? So there are some probability there. What is exact problem? Next. And these are the 4 principles I already discussed about superposition. See, qubit can exist in state 0, 1 or any combination of simultaneously, enabling crossing all states at once. All states 0, 0, 0, 1, 0, 0 like that. 0, 1, 1, 0, all states crossing of all states at once. In entanglement, qubits become correlated, measuring one instantly determines the other regardless of distance, enables quantum parallelism. I already told you some example. What do you mean by entanglement? Okay. Then interference, quantum space interference constructively amplify correct answer or destructively cancel wrong answer. Right? See, there are 2 waves. Okay. So positively combined, then it will create a large wave, right? And negatively, it will create destructive, right? So, okay. And coming to quantum system, exists in multiple states simultaneously until measured. See, these are the classical bits, and this bit is called cat 0. The cat symbol. We can use cat symbol in the quantum computing. Cat 0, cat 1, and alpha cat 0 plus beta cat 1. So this is general formula. Okay. Generate 2 bits, we can use this. All states simultaneously. So this is the formula we can use. Cat psi equal to alpha cat 0 plus beta cat 1 to form superposition. So anyway, entanglement already told you, and we'll skip this. Okay. Coming to interference, see, waves in phase, amplitude at correct answer are amplified, increase probability of right output. Okay. And coming to destructive interference, waves out of phase, amplitude cancel wrong answer are suppressed, decrease probability of wrong output. So there are several correct answers, there are several wrong answers, right? So correct answers will amplify and the wrong answers will be cancelled. So the probability of correct answer will be high at some stage. Okay? Right. See, from quantum computer algorithms, break RSA encryption, write post quantum security standards. So that's why we are working post quantum security algorithms, post quantum cryptography. And of course, we'll first see that algorithms. Okay. Then coming to, there are two most useful and highly used quantum algorithms, Sharp algorithm and Grover's algorithm. We'll work out these two algorithms today and we will see security issues later. Okay? So coming to Sharp algorithm, and Peter Sharp has developed this algorithm in 1994. And quantum algorithm this is quantum algorithm for time calculation of large numbers in polynomial time. So classical algorithms like general number field, let's see exponential of this Sharp algorithm order of log n. See anyway, classical factoring exponential time, impractical for large number, Sharp algorithm polynomial time.
Sir, we lost the PPT.
Okay, and choose a random number A in between 1 and n, A less than n and A greater than 1, right? For example, random number equal to I am choosing 2, right? So keep this note down because this algorithm we need to work out. I will also give another examples and we will write the steps. As per the example, we will write the steps. Okay. Then you can use Python program. So using this kit, you can work out. Right. And second step, find GCD of A comma n. Find GCD. So GCD of 2 comma 15. What is GCD? Greatest common divisor. What is the greatest common divisor of 2 and 15? 1 only. There is no common divisors, right? There is no common divisor. There is no greatest common divisor in 2 and 15. Only one. One is GCD for 2 and 15. Okay. Now we will take second step. Find the period. So now find the period R. This is very find the period order R of the function. Find the period R or order. So function is, just note down, f of x equal to a power x or a power r. F of x equal to f of r equal to
a power r mod n. This is the function to find the period or order of r of the function. See, this is the main formula and this is quantum part. This is only quantum part. This is the classical part. Okay, finding GCD is the classical part. So of course, how to find the GCD in computer? GCD of b comma GCD of a comma b. We'll apply that equation. Okay, right? Now, how to find this f of x? For our period is smallest positive integer. First we can take smallest value f of, I will keep it here. So a power r equal to 1 mod n. So once r known, and we have to find out r, period r, right? Once r known, then factors of n can be obtained from the GCD of a power r by 2 minus 1 comma n, and GCD of a power r by 2 plus 1 comma n. So these are the formulas we can remember. Okay, right. See, a equal to 2 we are selecting, we are choosing, right? So GCD equal to 1 and find period step. So compute powers of, this is step 2, compute powers of 2 modulo 15. Okay. See, x value 2 power, sorry, r value 2 power r, 2 power r mod 15. Right. Take this r value like this. Now you can find. Okay. So 2 power 1 mod 15. What is the value? 2. 2 power 2 mod 15. 4. 2 power 3 mod 15. 8. 2 power 4 mod 15. Right? 1. Okay. So 2 power r mod 15 equal to 1. So we stop there. So now we can take r value equal to 4. Right? R value equal to 4. So period value we are finding 4, or order value of that function is 4. Now once you find that R value, right, now we can go to third step, step 3. We can apply a power r 1 mod n and GCD of like this we can apply in these equations. Okay. So go to that step. 2 power 4, this step, 2 power 4 equal to 1 mod 15. Okay. So the period r is, r equal to 4. So a power r by 2, a power r by 2, what is a power r by 2? Equal to a power 4 by 2 equal to 2 square, that equal to 4 only again, right? So this is 4. So find factoring using GCD now. Okay, so GCD of 4 comma 4 minus 1 comma 15 equal to 3, equal to 3. So GCD of 4 plus 1 comma 15 equal to 5. See 3, 15, GCD 3. Greatest common factor is 3. And ఇక్కడ 5, 15. What is the greatest common factor? Greatest common divisor 5. So we are finding 3 and 5 GCD. Then we compute now. Therefore, these are the two factors, right? Now we can write 15 equal to 3 into 5. Okay, these are the factors for 15. So in this involve classical part and quantum part. We are finding period using quantum part, and finally again classical part. Okay, finding GCD. So these are 3 steps in Shor's algorithm. Okay, now we can work out another by taking another one. For example, you can take n equal to 21. So apply the same steps. So n equal to 21. You can use this. Just it. See n equal to 21 and choose a random number. This is the first step. So random number A, right? A in between 1 and n. So I'm selecting A equal to 2 now, right? Now what is the equation we are applying? What is the equation? A power r mod n. Okay, so we need to find r, right? So r value you can find. How to find r value? How you are finding r value? Period value, that is the main. Okay, r a power r mod period values are finding. Okay, 1 2 3 4 like that we can find. A power 1 mod 21. A power 1 means 2 power 1. Okay, what is the value? 2. 2 power 2 mod 21 4. 2 power 3 mod 8. 2 power 4 mod 21. What is the value? 16. Okay, and 2 power 5 32 mod 21 11. Then 2 power 6 64 mod 21 1. Okay, it is 1. Now you fix r value here. R value is 6. Okay, so for small integer number, factoring is we can find easily r value, but it's a large integer value. Finding it will take more number of steps. That is the reason why we can use quantum, right? Otherwise, by simply finding r value, 1 or 2 steps, you can go for classical computers. Okay, factoring large integers, finding factors for large integers, only we can use Schwar's algorithm. Okay, GCD anyway classical computing, right? Finding r value, that is called period value or order value, we can use quantum computing, right? So once you find this, then what is the formula we are using? Formula, what is the formula you are using? A power r minus 1 comma n, GCD of r by 2, right? A power r by 2 plus 1 n. What is the value? And the చూడండి మీకు 6 by 2 and 2 power 6 by 2 minus 1 n 21. 2 power 3 8 minus 1 7 721. GCD of 721. What is this GCD? 7. GCD of plus 1. Okay, 9 21. What is the value? 921 3. Okay, so the prime factors are n equal to 7 into 3. So 21 equal to 7 into 3. So like this we can find the r value, right, and find the factors of that n using Schwar's algorithm. The same thing we are providing in the slides. ఒకసారి చూపిస్తాను. Right, see. See, measuring qubits, of course, check conditions, r must be even. Of course, this is one condition, r value must be even, not odd, right? Okay, we should not take r value odd. For example, a power n by 2 we divide, right? R by 2 we divide, so it will give some fractional. That's why you don't select that odd number. Only even number you can select r value. R must be even, and a power r by 2 not equal to 1 mod n, right? So if condition fails, restart with a new r value. Okay. So until you get 1, right? So that is those are the steps we are performing here till we get 1. Then stop there, and we can take that R value. Okay. Then coming to compute factors, factor R1 GCD of a power R by 2 minus 1. Already we have seen this in example, right? And factor 2. This is factor 1 and factor 2 GCD of a power R by 2 plus 1 n, and these are non-trivial factors of n, right? Not trivial factors. Okay. See, so this is the process which are following in Schwarz algorithm. See, I told you there are 2 parts in computing, right? So classical computing and quantum computing. Okay. So coming to this classical computing, classical pre-processing, right? Finding GCD and finding quantum superposition. So we are finding R value, period value, right? And quantum phase estimators. And this is by using these two, we find R value, right? And measuring that value. So for example, 15 equal to 3, 5, measurement of that factors. And classical post processing, factors of n, finally we get that factors of n. So the same steps we performed in these steps, example, right? See here, once again, the same example, already we have worked out on the board. See, given n is a number, right? And integer number, we need to find factor. To find R such that 2 power R equal to approximately 1 mod 15. See, computing 2 power x or whatever it is mod 15. So we are taking x value or R value, period value, 0 starting from 0 to some number, and 2 power x mod 15. Then once you get this period value, right? 4, 1 equal to 1, right? Now we consider this value x as a period value, okay, or order value. See, these are the classical post-processing steps we are performing, okay. So classical pre-processing, finding GCD, post quantum processing, finding R value, okay, period value, and the classical post-processing, finding these 3 steps, performing these 3 steps. So we can, after once we find that R value, now we can apply this formula, and we are getting 4. Then GCD we can find by using this formula, a power R by 2 minus 1 and n, and a power R by 2 plus 1 and n, and we find GCD so that we can find the factors. This is the final result, 15 equal to 3 into 5. So these are steps involved in Schwarz algorithm, nothing else. Okay, the same thing we can implement in Python, and we can use whatever the tool, quantum software tool, right? IBM tools are available. Okay, so we can use freely download Qiskit IBM tool, and Python. There is small program. It is very small program. It's already there. You can apply these formulas and give input values. Give some large integer value. Now we are taking 15 or 21 or 33, something like that. We can give some large integer value, choose a random number, a some value, and automatically it will find all the factors. Okay. Right. So something I want to tell you, because for example, so this is about Char's algorithm, an example, right? So coming to another algorithm, quantum algorithm, Grover's algorithm. So Grover's algorithm, this algorithm is used to find or search, is searching algorithm. You know, the linear search and binary search algorithms in classical computers. Okay, so you can apply a linear search algorithm, a linear search technique, to find a desired item in the list of items. For example, there are 10 integers, right? And I want to find this 15 integer is there in the list of integers or not, right? So we can apply two types of searching techniques in classical computing. One is linear search, also called as sequential search, right? Sequentially, we can perform searching process from first element to last element, right? So if the element is at the last locations or element is not there, you could not able to find, what is our time complexity? Order of n elements are there, order of n. You go of n, right? If the element is somewhere in the middle locations, right? So big O of n by 2. Okay. So average searching process takes n by 2, or worst case takes order of n. But coming to this Dover's algorithm, quantum algorithm, so let it be average or worst case or whatever it is, there is no case. So it takes root n searches or what do you call comparisons. Okay, root n, right? Generally, it's order of n. It's polynomial or exponential. Okay, polynomial, right? So root n, it decrease all the comparison searches. So that is the purpose of using this Grover's algorithm. So anyway, we will see this algorithm, and we just go through this algorithm. Quantum algorithm for unsorted search, unsorted databases. Just simply write Grover's algorithm used to search data in unsorted databases. This is used to search data in unsorted databases. Search the desired item in unsorted databases, large databases. When there are large databases, we can use this Grover's algorithm, not for small databases. Anyway, linear search can be used for small databases, right? Smaller set of values. And if the data is sorted, we can use binary search in classical computers, right? So we can divide every time so that we can reduce the number of comparisons by using binary search, right? If the data is large the database is large database, then only we can go for quantum Grover's algorithm. Otherwise, no need. You can go for classical computing, right? See here, classical search takes order of n, and Grover's algorithm takes order of root n, quadratic speed. We decrease that, right? These are the three key mechanisms in Grover's algorithm: superposition, search all states at once, and interference, amplifies the correct answer, choosing the correct answer, right, in high probability, okay, and amplitude amplification, boost probability of success. See, there are two operations we need to perform in Grover's algorithm: oracle operation and diffusion operation. These are the two operations we can perform. We'll see that operation by taking example, and we'll see algorithm. See, what is oracle? Just to know this, what is oracle operation? A quantum black box that identifies the correct solution by flipping the phase of the target state. So there are these, for example, these are the states. Okay, my desired item is 10. Okay, now we can flip it. So this block, what the Oracle operation will flip it. Okay, positive to negative, right? And remaining all these are positive. This is only negative. Oracle marks 10 phase flip minus amplitude. It will represent minus amplitude. So it cannot reveal that this is the answer. This is the correct answer, right? It will identify, okay? It will not reveal it, right? Then every time percentage it will increase. Okay. So see, Oracle does not reveal which state is correct among all these 4 states. It only flips the phase of the target plus x to minus x, right? The plus value to minus value. All other states remain unchanged. It will not change any other state. And phase flip is invisible until combined with the diffusion. So by using Oracle and diffusion operations, then only it is possible to find the correct answer. So mathematically, Oracle equal to, this is the formula, W equal to target, desired item. Okay, right? Now we can see best example. Then we can come back to this Grover's algorithm. The steps anyway is easy to know once you solve the problem. You note down one problem. Choose. We have 8 lockers. For example, there are 8 lockers and 1 locker contain money. All remaining 7 lockers does not contain money. Then how to find which locker contain money, right? So we need to find the high probability which locker contain money, right, by using Grover's algorithm. We'll see that example so that we can understand. Later we'll come back to this operations and right algorithm. You can easily understand. Locker 1, 2, 3, 4, 5, 6, 7, 8. And contained money or price, whatever it is, contained money, no. Locker 1 does not contain money. Locker 2, no. Locker 3, no. Locker 4, no. Locker 5, yes. Locker 6, no. Locker 7, no. Locker 8, no. Okay. So now we can know that locker 5 contains money. Okay. So Oracle operation will find it. This locker contains money, but it will not reveal it. Okay. It will flip it. So positive to negative, right? Now the money is in locker 5. So classical search without any information. So what you do, we need to check about 5 lockers and in the worst case 8 lockers. And okay, so we need to check classical search. How to perform classical search? You check it whether there is or not. No money, no money, no money. Yes, money is there. Okay, we stop. For example, in 8 there is a money or no money in all the lockers. Right? How many searches we need to perform? 8 searches. 8 comparisons we need to perform. Okay, right. So coming to Grover's idea, the Grover's idea is, so instead of checking lockers one by one, represents all lockers simultaneously. We represent all the lockers simultaneously at once, right? How to represent all lockers simultaneously at once? Initially, we give equal priority, equal probabilities to all the lockers. 8 lockers, 100%. What is the percentage? Sharing equal priority, 12.5. Okay. Now we give equal priority, locker probability. Locker 1, 12.5 probability percentage. Locker 2, 12.5 percentage. So like that, all the lockers 8, same. Okay. Now we are providing equal probabilities, right? So for all the lockers first, okay, right? Now what we can do, we can perform step 1 Oracle operation. Here it is the main step. Once you give equal probabilities in percentage, 100% to all the lockers, now we can apply Oracle operation. So Oracle recognize the correct locker. It will identify the correct locker by using that black box and using equation. Okay, right? Yes, it is there or not, right? Money is there or not. So once it's decided, okay, right, locker, it does not reveal this answer, of course, directly, and instead it marks locker 5 by changing its face. Conceptually, what it will do, 1, 2, 3, 4, 5, 6, 7, 8. So plus, 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 minus, it will flip, plus, 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 like this. It will flip that value, plus to minus. Okay, right. So now only this locker 5 gets a minus sign, of course. Then step 2, amplitude amplification we have to perform. Okay, the diffusion operator uses this quantum interference, of course. What we have to do, lowering probabilities of wrong lockers and increasing probabilities of correct locker. Lowering probabilities of wrong lockers and increasing probabilities of correct locker. Okay, so how to do it? See, for example, for this one we can decrease, 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 right? Now we can increase it, probability, decrease, 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 right? So probability we are increasing to this 5 locker, because already Oracle operation identify that we're increasing probabilities. So like that we can also increase later, right, to find the correct answer, right, already known to the Oracle operation. Okay, so 1%, 1, 1, 1, 93%, 1, 1, 1%. See, 100%, right? So we can find the correct answer with the probability of 93% using Grover's algorithm. Okay, if we increase lockers like that, go on, right? So we can use Oracle operation and diffusion operation. It's already defined, these 2 operations. We don't need to do anything. We can only write the program, apply in Python, okay, give input and get the outputs. Okay, so for finding the desired item in unsorted databases, we can use this Grover's algorithm. Okay, so anyway, you can go through the steps later. So these are the only superposition finding, then performing Oracle operation and diffusion operation, right? And increasing the probabilities and decreasing the probabilities to non-desired items, right? So this is something about Grover's algorithm. These are the steps involved in Grover's algorithm. Okay, so create superposition using Hadamard gate. We can create superpositions, right? So all possibility of the states, possible states, and Oracle mark target answer. Oracle operation will mark the target operation, right? And the remaining are unmarked. It means flip that target desired operation. Okay. Then amplitude amplification is diffusion operation. So we are giving probabilities to each and every one, increasing the high probability, so that at one state we stop after getting the high probability and the correct answer. And repeat root power n iterations. We need to perform these steps, right? And measuring anyway, once you repeat it, then finally we are getting that correct answer. So correct solution found. These are the simple steps in Grover's algorithm. Right. So some of the applications of Grover's algorithm: database search, find records in unsorted databases in order of root n, rather than finding order of n in classical search. Right. This is one application. And password cracking, break symmetric key encryption. Example, for example, AES 128 reduced to 2464. So root 128. Okay. So that's why nowadays we are doubling that key value, 256. Right. So anyway, there is a threat to this AES algorithm and DES algorithm. Right. See, Grover, what you call Shor's algorithm. So there is a threat to RS algorithm. So because RS algorithm we are using, right, prime factors, very less prime factors. Right. Once original quantum computer, we are working on original quantum computer, it's very easy to hack RS algorithm. That is the reason. So we need to care about, right, implementing this Shor's algorithm in original quantum computing. Okay. So there is a threat to RS algorithm and public key cryptographic algorithms like Diffie-Hellman, or there are some public key cryptographic algorithms. So any public key cryptographic algorithm, there is a threat by Shor's algorithm. This is the problem. So coming to encryption algorithms, symmetric encryption algorithms. So there is a threat to by using this Grover's algorithm. Okay. So this is AES and DES and right. These algorithms are encryption symmetric algorithms, right? So there is a threat using this Grover's algorithm. Okay. Attack hash function because cryptography when use this Grover's algorithm, immediately it will find. Okay. So that is the problem. Right, AA search, this is another application of Grover's algorithm, and optimization, solve NP hard problems faster via quantum search strategies, and pattern matching, search, text data quantum speed will increase, right? So by using this Grover's algorithm. So advantage of these quantum algorithms: exponential speed up, quantum parallelism, and quadratic search speed up by using Grover's algorithm, and exponential speed up by using Shor's algorithm, and complex problem solving. So tackle optimization and simulation and ML problems beyond classical limits. So these are the sum of advantages of using these algorithms, quantum algorithms like Shor's and Grover's algorithm. Right. Anyway, so challenges in quantum computing: hardware limits are there because hardware is more costly. Hardware limits. Then error correction. Quantum operations are error prone, fault tolerant. Quantum computing requires thousands of physical qubits for logical qubits. This is another challenge. And another challenge: costly and scalability. Quantum computers require extreme cooling near absolute zero and minus values. Right. That is the reason. Right. This is another challenge using quantum computers. The cost of hardware maintenance and of course infrastructure is more, right? And decoherence. So qubits lost their quantum properties when they interact with environment. See, for example, waves. So when you try to catch the wave, right, measure the wave speed or something, it will collapse. Okay. So we are using electronic circuits in classical computers, but quantum computers separate technology, semiconductor technology, right? Okay. Quantum physics involved, right? There are hardware part. Okay, so measuring these quantum bits is highly right costly, and we should not anyway. There must be proper quantum algorithms, right? So to handle or to measure the quantum bits, right? Okay, and where is that PDF? PDF open. And see, within 5 minutes, we will just go through what are the security issues you may, right, get in quantum computers. See, already I told you, Shor's algorithm, right, and the security impact is many public cryptographic systems rely on the difficulty of these problems, including RSA cryptography. These are the public cryptographic algorithms. There is right security threat on these algorithms. Okay, when Shor's algorithm really implemented on real quantum computers. So coming to Grover's algorithm, please up. So already told you. So this is there is a threat on symmetric encryption algorithms like DS and AS algorithms, right? So this is another security threat, security issue in quantum computers algorithms. And quantum phase estimation, right? And coming to many quantum algorithms, for example, a core subroutine used in many quantum algorithms, factoring, quantum simulation, and scientific computations. And these are the another problems such scheduling, logistic problems, resource allocation problems. Okay. Major security issues you can identify here. Like please up. Security in vulnerabilities. The biggest concern is the potential compromise of current public cryptography at risk. Right. For example, secure web communications, HTTPS, digital signatures. So maybe forged all the digital signatures and quantum computers using these quantum computer algorithms. Harvest now and decrypt later attack. This is a attack nowadays. People are thinking, right? Attackers may collect encrypted data today. Now I don't want to decrypt it. I will keep it, right? I will keep that data and store it until quantum computers become powerful enough to decrypt it. So when original quantum computers existence, then we use that data. So that is a major major problem to government records, okay, etc. So financial data, stock market. So these are some of the security issues. Quantum computing infrastructure risk, right? So you can share it, okay? So go through some security issues, right? So mainly using quantum algorithms like Shor's algorithm and Grover's algorithm, and security threat is there for public key cryptographic algorithms using Shor's algorithm, and security threat is there for symmetric encryption algorithms like AES and DES algorithms. Okay, so to avoid this, I don't know what will happen, right? So anyway, original quantum computers and an increasing qubits. So only for some applications we can use, not for all the applications. Anyway, and people are thinking that on quantum computers, right? So we can use quantum computers to solve all the problems, not all the problems. Everyday problem we can solve and we can perform using classical computers only, right? So without classical computers, only quantum computers we cannot use, right? Okay, so because more costly hardware problems and okay, there are so many problems. Only for some problems, to solve some applications or some problems, you can use quantum, like drug discovery problems, stock market, right? Medical health records. So only for such type of large databases, large data, right? We can use quantum computers, right? So thank you for giving this opportunity. So I hope I have given some input using quantum algorithms like Shor's algorithm and Grover's algorithm. Right? You please go through some more because it's a new subject. Okay, new technology. We need to improve day to day. Okay, at one day or one moment, so it's not possible to know the entire quantum technology. Thank you very much. Thank you.
We sincerely appreciate the time and effort dedicated for making this session both informative and engaging. My heartfelt appreciation goes to all the participants for their active involvement, enthusiasm, and meaningful contributions, which played a vital role in making this session successful. Once again, we express our sincere gratitude to our distinguished speaker, Dr. K. Venkatrao Garu, for delivering an inspiring and enlightening session. The knowledge and insights shared today undoubtedly benefit us in our academic and professional pursuits. Thank you all for your presence and participation. Now, it's a great pleasure to felicitate Dr. K. Venkatrao Garu as a token of gratitude. I request all the dignitaries to join the felicitation.
Extra cricket series, sir.
సార్ నేను